It is my pleasure today to introduce our featured speaker, Victoria Stein. Victoria wears many hats. She is an associate professor in the School of Information Sciences at the University of Illinois at Urbana-Champaign, with affiliate appointments in the School of Law, the Department of Computer Science, the Department of Statistics, the Coordinated Science Laboratory, and the National Center for Supercomputing Applications. She completed both her PhD in statistics and her law degree at Stanford University. Her research centers on the multifaceted problems enabling reproducibility in computational science. This includes studying adequacy and robustness in replicated results, designing and implementing validated systems, developing standards of openness for data and code sharing, and resolving legal and policy barriers to disseminating reproducible research. Her talk today is titled Rethinking the Scholarly Record, Facilitating Reproducibility of Computational Results. Please join me in welcoming Victoria.
Okay, thank you so much for the invitation and for welcoming me here. It's a real pleasure, and one of my favorite parts of my job is actually being able to come to events like this and address a broad variety of folks from all aspects of university research. So this is a real pleasure. As Nancy mentioned, what I'd like to do today is talk about and sort of think about what should comprise the scholarly record for the types of research that we're doing today. Thinking about how we actually disseminate research that we carry out today, and my fundamental argument is there's a mismatch in our dissemination today to the research that we're doing and the outputs that we're doing. And I call that mismatch, or sort of put it in this bucket of view reproducibility. So what I'd like to do is build up why I think we have these issues around view reproducibility today. We have many editorials coming out in Science, in Nature. We even have The Economist or LA Times, whatever it is, popular press, New York Times talking about problems of view reproducibility in science. So what I'd like to do is take some time to unpack where those issues might be coming from, what they mean, what those different conversations are referring to, in my opinion, and then talk about steps that are happening and that we can take that actually start to resolve the problem, not from a perspective of we need to change everything we're doing and science is really different now, but in the sense of how can we realign our practices with the norms that we've held for hundreds of years in science. So I'll finish with some sort of open issues and recommendations in that area. And just a note that my slides are on my website. If you prefer to, follow along on your own tablet or laptop, please feel free. And I'm perfectly happy to have questions during the talk, and I would like to leave time, a reasonable amount of time afterwards for questions as well. So I'm very happy to discuss. Okay, so technological change. So I think people in this room are familiar with these changes, or at least some of them, but I think it's very helpful to parse them out, and then I can start to build on them for the remainder of the talk. So the first change that I think is impacting this sort of discussed notion of reproducibility is the huge amount of data that we're now dealing with in all sorts of aspects of research across the academic landscape. So we have not just scale in terms of more and more research, more and more data that we're collecting, but we also have different types of data that we're working with. So for example, very high dimensional data, where the number of variables outstrips the number of observations, very different than the traditional types of data that we've seen and for which the methods have been developed. In parallel to that, we also have incredible increases in computational power. So, for example, we can do things in a silicon system to emulate or simulate the real world in ways that we've never done before. And of course, that allows us to ask many more questions and do all sorts of new types of investigation that just weren't available even a few years ago. So both of those, I think, people are aware of in the room. The other one that I think is just as important as the first two is we're now seeing the rise of software as a medium or modality for our research. So we actually are seeing real scientific contributions, for example, in methodology or in application of software that exist only in the software itself. And that is something that is new and I think makes us sort of think about software as one of the places where discoveries reside. So I have a photo here of Laura Patcher, who is probably known to people in this room, a professor at Berkeley, who I believe has just moved to Caltech. So I just grabbed this screenshot from a keynote he gave, and I was just watching on YouTube, and he's talking about how the software contains what he calls ideas that enable biology. So this is starting to sound like the scholarly record, right? That's supposed to be where our ideas are contained and published and disseminated to the community. And yet, we don't see an easy way to access and understand these ideas that are in the software itself. Okay, I'll mention two other, just for completeness really, I'll mention two other aspects of technological changes that are driving some of these issues around reproducibility. The first one, of course, is digitization and communication in the internet. We're now able to make digital objects much more readily available, both as ingest for our research and also as disseminated products from our research. And then the other piece that I'll mention is how that digitization and that access, say for example, over the internet interacts with intellectual property law. So now we have this host of issues as researchers that we need to address when we're, like I said, either taking objects from the internet or contributing them to the internet that we just never, 20 years ago, we never would have thought about. So I'll touch on the intellectual property law in a few minutes in my talk. Okay, so as you've seen and probably heard, there are a number of different conversations going on around the issue of reproducibility. One of the issues that has, or sort of the fields that has grabbed a lot of the spotlight has been issues around reproducibility in psychology, for example, in social psychology. I put this slide here so that because I found it very useful to identify different types of reproducibility that people are talking about. So my sense is that the conversation in psychology is very different to the conversation around reproducibility in preclinical research, for example, which is different again to computational research, which underlies many of the issues. So the first way that I think about reproducibility is what I call empirical reproducibility. So in this sense, this is, in a sense, traditional, if you think of traditional bench work or wet lab work, how would I actually reproduce this work? There's, in a sense, sort of thinking about this narrowly, there's, these are traditional problems that there have been solutions and discussions to over many, many years. So how do I actually do sort of a real physical experiment, and how do I replicate that or understand that in a different setting? So that's what I'm calling empirical reproducibility. That is quite different to what I'm calling statistical reproducibility. So encompassed there would be issues around experimental design, for example, power of your test, and would you really expect your results from one sample to generalize to another sample, which of course is fundamentally underlying the reasons why we might be doing the research in the first place. Okay, so those two are quite different to computational reproducibility. So in computational reproducibility, which is where I situate most of my research, can you actually regenerate results and claims that have been published using data or software either from the researcher that may have been written independently? So can I actually redo that computational pipeline that has led to the claims itself? And what I'll argue going forward in the talk is that this underlies transparency in a very necessary and important way for modern research. Okay, so let me dig into these a little bit more. Okay, so I put a screenshot of a commentary published in Cell Reports. So it's just a couple of pages called Sorting Out the Facts and Deviling the Details. So my background is not in biology, but this was a report from two biology labs, one at Harvard and one at Berkeley, and they had a joint grant for which they had set aside 2 months at the beginning of the grant to ensure that the actual cell output from their two labs was indistinguishable, so that there wasn't, say, a unique signature that could identify the output is coming from Stanford or coming from, coming from Berkeley or coming from Harvard. And the point of the article is that it took them actually 2 years to reconcile the output such that you couldn't actually just immediately tell when you looked at it to do the analysis which lab it was from. And so I put this up there as an example of how difficult it can be to reconcile these empirical pipelines. And as it turned out, I think they were using a centrifuge differently in their process. So something that each lab had assumed was obvious and everyone did it that way. And but they actually took the time to really kind of dig why the processes were really different, and it took an extraordinary amount of time for them to do that. I also put up here a screenshot, which I don't think you can see it very well, but that's a National Academies workshop from last year called Reproducibility Issues in Research with Animals and Animal Models. And the reason I put that up there is this is, in some sense, a unique issue around reproducibility that happens when, in the empirical context, when you have animals in your research. So one of the questions that came up there was, well, how do I value reproducing a study when, for example, I'm killing animals in the study, which is very different to, say, regenerating computational results ethically. So the issues that attend to different aspects of reproducibility are very much grounded in the types of research and the types of questions that underlie the work itself. Okay, so statistical reproducibility, I won't spend a lot of time here, but there are many issues with things like what's been called p-hacking, Jerry Simonson labeled, running many different statistical tests until you sort of get the one that looks like what you want the output to look like, right? So this is all sort of very bad practice. And doing so and not reporting the other tests that you've run makes it much less likely, of course, that those results will actually hold up and generalize in new samples as you might like them to. So just things like all these kind of statistical traps, how have you handled outliers, what type of model specification have you used, is it appropriate to the scientific questions that you're trying to ask and answer. So that sort of breaking this sort of statistical integrity in the work also would cause issues of irreproducibility and also have a number of different solutions attended to it. If you contrast that with, say, the cell reports folks who were trying to reconcile their physical analysis processes. Okay, so the final aspect of reproducibility is computational reproducibility. So this one is new over the last, say, 10, 20 years. And so I'm going to step back and take some time to really build why I think this is something different. And I will mention that in empirical, statistical, and computational reproducibility, of course there's overlap, right? Of course computational methods start to bleed into others. But as sort of a pedagogical device, I found it very useful to sort of pull them apart. Okay, so if we think about the scientific method, we all know that there's traditionally been two branches. And the first being deductive reasoning, like mathematics and logic, as a way to discover new properties. And this, of course, falls short if you want to do something like predict where to plant your crops next year based on the previous flooding of the Nile, for example. And so we have empirical or inductive reasoning as the second branch of the scientific method. So these have been around both hundreds of years, of course. And empirical research, now we use statistical analysis of controlled experiments to try and understand inductive conclusions. So there's a lot of talk, and I'm sure you've heard it, around technological changes, as I've described them, underlying new branches of the scientific method. So we have this ability to do very complicated simulations on machines. This is leading to a third branch of scientific investigation or scientific method, and the data deluge leading to this fourth branch of the scientific method. So I snuck in a little question mark there, because what I'd like to do is argue that we're not quite there with the computational aspects to really call them third or fourth branches of the scientific method. Okay, so here's why I think that. So if you step back and you try to understand why we have a scientific method and what problems it's trying to solve, what I argue is it's really about the ubiquity of error. So as we're carrying out these experiments, we could be making errors anywhere, right? In understanding the processes, in your implementation, in deriving conclusions. I mean, this is the nature of research. It's, we don't know the answer, and we're, essentially trying to figure it out. So in the deductive branch, you don't publish a mathematical claim without giving the underlying reasoning on why you think it's true. And so over hundreds of years, there's a very well-defined notion of what that means, and it's called the mathematical proof, and that would go with the mathematical finding itself to make it transparent how that claim was actually derived or why the author thinks it's true. In the empirical branch, there's an entire machinery of hypothesis testing, use of appropriate statistical methods, as I discussed a little bit, and a very structured way that you would communicate that to the community. So if you try to publish a paper and you leave the methods section blank, it's just immediately going to get rejected. They don't even look at it. So these types of things have had hundreds of years to percolate on what those appropriate dissemination standards are. And they bring to the research a level of transparency and verification that's very important for rooting error out of the discovery process. So why should I believe your claims? Well, here's why you should believe them. You can actually give the actual underlying evidence and the chain of reasoning that led to those claims. So here's what I'm asserting. The computation presents only a potential third or fourth branch of the scientific method until we develop comparable standards. So as I said, it's really only been 10, 20 years that we've been thinking about this. The first two branches of the scientific method have hundreds of years to come up with their standards. But I believe this is a challenge that's before us now. So there is a phrase, really reproducible research, that was coined in 1992, or possibly earlier, but at least on his website, coined in 1992, by Emeritus Professor John Clairbeck, who came from geophysics. And my advisor was David Donahoe, and he is in the statistics department at Stanford, and he coined Clairbeck's ideas as follows. That the idea of really reproducible research is that an article about computational science in a scientific publication is not the scholarship itself, it's merely advertising of the scholarship. The actual scholarship is the complete set of instructions and data that generated the figures and the tables and the claims that you're making in that publication. So that goes back to where I started with the importance of software as a first-class scholarly object containing results that are very important, crucial for verification of claims and understanding claims that are being made in the community. Okay, so sometimes I get a question here about, well, who cares if you can actually run someone else's code on their data and get the same figures and tables that they publish? That doesn't mean much, and it certainly doesn't make things right. You can run terrible code on flawed data all day long and get the same tables and figures in the paper. So all of that's true. So the way that I think about it is we still need to be able to do that. We still need to be able to at least inspect the code and be able to inspect the data that underlies those claims that are being made. And the reason is because if you do go out and you do independently rewrite software and re-implement those particular methods in that paper, regather the data, and reproduce the experiment in a fully independent way, I can guarantee you will end up with at least slightly different answers, slightly different numbers. And so then the question becomes, how can I actually compare and understand the differences between the two implementations if I can't see one, if it's opaque? So we still need that level of transparency around the software, around the data, the steps. You know, if you think about it in terms of like a mathematical proof, or use that analogy, what were the steps that actually led to those claims, so I can do that difference and understand why they're different. So then I can say I have supporting evidence with my independent re-implementation, because I know that I'm close enough in a sense because I'm able to reconcile the two methods, or I have counter evidence. I'm far enough away and I've understood the two processes, so I can say that this is really something that's meaningfully different and we should be taking a look at this. Okay, so the answer is both are really important, and yes, it's true that running someone's code on someone else's data and getting their same results is not an advancement of science, but it is, I think, necessary to advance science when we actually start reconciling different results. Okay, so if we go back to 1942, to Burtons norms, which are not without controversy in their own right, but I put them up here because what I'd like to do is ground responses to what I've outlined here, this credibility issue around computational science, and see if there's any guidance in norms that we use and we respect in the scientific community. So Burton put together 5. Communalism, scientific results are the common property of the community. Universalism, all scientists are able to contribute regardless of where they come from or who they might be. Disinterestedness, we're acting for the benefit of a common scientific enterprise rather than for personal gain. Originality, contributing something new when we publish our claims. And skepticism, scientific claims must be exposed to critical scrutiny before being accepted. So I lean on skepticism and to some degree communalism when I argue for increased exposure of computational pipelines in the scholarly record when we're actually publishing scientific claims. Okay, so this is Robert Boyle. He, in about 1665 or 1663, was the first person to say we really need to embed notions of reproducibility within the publication itself rather than, writing a letter to the author saying, how did you do this? Help me sort of figure out how to implement your experiment. It should exist standalone in the publication. So that's, in a sense, our heredity around this problem. Can we make the publication standalone so that you can actually go through, reproduce claims, whether you're doing it independently or whether you're reproducing by running the code on their data and so on to get the results? Can we do it in a transparent way that allows us to root out error? The whole point of the scientific method. Okay, so how does this impact the scholarly record? Okay, so here's what I think. So we need to rethink what we disseminate when we disseminate claims. So we want to be able to regenerate these findings. So thinking about what items would travel with a claim. And my argument is that the methods section in a scholarly publication can't possibly contain all the information you might need to reproduce a computational result. It probably doesn't have information about how the statistical models or whatever inference techniques were being used were actually implemented in software, what the parameter settings were, how many tests were run, for example. Do I understand exactly the vagaries of the data set itself as was collected? What were the treatment of outliers or pre-processing of the data set? A lot of that is missing. And it's not missing for nefarious reasons, it's just our own way of doing research has evolved, and the scholarly publication needs to evolve to catch up, to make it so that we can really root out errors. So we need items relied on in generation of results, items required for independent replication and reproducibility. So I'm thinking about things like running a whole lot of tests and then kind of not reporting those tests. So really that's something that that's part of the pipeline, right? That's something that allowed us to get to particular claims and is something that should be out there and being available, especially since that impacts the interpretation of statistical significance of the findings. Okay, so what are these items that are supporting the scholarly record? So I believe these digital scholarly objects, obviously the article, text, but code, software, data, workflow information. So if I have your code and it's this sort of jumbly bundle of functions, I still need to know information like what order did you apply these functions in, what were your inputs, what were the outputs, what was that sort of chain of reasoning as you went through and did the computations. The details of the research environment or computational environment, that might be relevant to understanding those results. There are also material objects. These to me fall in the bin of empirical reproducibility, so I am touching on them less in this talk. Reagents, lab equipment, instruments, historical artifacts, and so on. So all of this we can start thinking about in this larger context of reproducibility. So if I'm sharing these objects, we need to also think about them as just as important as if we're sharing a publication. So with a publication, we know things like what journal it was in, volume, issue, pages, and how to cite this. We have standards. And so what would that mean if I'm sharing, say, a piece of code that supports claims that I'm publishing or a data set? So many people have been thinking about these issues. I'm certainly not the only one. So I wanted to mention some some of the responses, and there are responses from many different angles to these issues. One of the key angles is in computational infrastructure, in tools and in software that people are using to support their research. So I put some tools together here. These are all hot linked if you're interested. Some of them are just like wonderful and fantastic. Well, they're all wonderful and fantastic, but they're worth your time to sort of click in and have a look if you don't know them all. And in my mind, they sort of fell into three categories here. So it seems to be a bright line around publication. So there are tools that will assist in dissemination of digital artifacts like code, data, and so on after publication. So I'm calling that dissemination platforms. And I've been doing some work in research compendia, for example, to try and build platforms that travel with the scholarly record to make coding data available. There are also an entire battery of tools pre-publication to sort of kind of help capture those key pieces of information that aren't being captured in the publication, so that they can be made available at publication. So they don't have to necessarily be public before publication, but at the time of publication, these workflow tracking research environments have allowed you to capture the information that you might want to disseminate when you get to the point of publication. So sort of making your life easier. If you've ever had to sort of get reviewer comments and then you have to go back to figure 2 and regenerate it, and you're just like, gosh, and you kind of have to start again. That's when the sort of the workflow tracking underlying the research pipeline is probably broken. It would be much easier if you had something where the workflow is in a tool or sort of laid out, and so going back to something like figure 2 and regenerating it is really only a few clicks or a few keystrokes, for example. So coping with reviewers' 2's nasty comments is much more seamless that way. Okay, and then there's another class of tools around embedded publishing, and I've thrown some in here where they're really trying to deliver the output as an object that is not just a PDF narrative that you would read, but actually has integrated into it, say, for example, code or data, or at least links to coding data so you can regenerate results in words. So sort of that's a hybrid. Okay, so one of the things that I've done with Research Compendia, so Research Compendia is very much kind of a research platform for me. We put it together to provide one stable website to support a publication in the scholarly record where you could grab code or grab data. So the idea was linking the data, code, workflow to that published claim, and understanding what is difficult about making that link, what's easy, how does it persist, what additional information do we need. So really trying to understand what it would mean to make these digital scholarly objects available and how to embed that more seamlessly into the community. Okay, so here's one page, for example, and this is a publication from PLOS One that I didn't choose for any particular reason, but the idea is this code and data abstract. It's not meant to be the abstract from the paper, but a discussion of code, data, and relevant information for people who may be interested in using the code and data. And then you can see these buttons down here, clicking for code, clicking for data. You can also click for the article, this is an open source publication. And then there's licensing information as well, which I'll get to in a moment. Okay, and it's all open source and sitting there on GitHub, so you don't have to use necessarily our website, but you could actually just go and stand this up and take a look at it, what's going on sort of underneath the covers. Okay, and there's the MIT license that we put all of our Research Compendia platform code under, and I'll just defer the discussion of licenses for a couple more minutes. Or now. Okay, so with licensing information, that's something where traditionally we don't have a lot of emphasis on things like intellectual property at the researcher level. We're familiar with copyright over our narrative to the publication when we actually go to the point of publication and interact with the journal. But as you're sharing data, similarly as you're sharing narrative, or sharing software, or sharing workflows, also copyright information attaches and travels with all of this information as well. So we need to attend to all of that as we're actually sharing it. Okay, so open source software, so that's a picture of Richard Salmon, who developed the first open license for software, and that was the GNU public license many, many years ago. And it was extremely innovative in the sense that as you share software, you have copyright attached to that software, preventing other people from, say, literally copying it, creating derivative works, and all these things that we would really like to do with software. So in the context that Stallman was dealing with, he was seeking to build a community where software was shared openly, and source code was openly shared, and there was that level of transparency. So developing the open source license was a way of having an extra piece of information traveling with the software that just gave terms of use, and basically permissioned people to go ahead and use it rather than having to ask the author, ask Stallman, can I please use it? Yes, and then it's legal. Right? So he just sort of pre-permissioned. And it was so successful that now there are, of course, hundreds and hundreds of open source software licenses out there with many different cases and so on. So what I thought about was, well, so that's for the open source software community, so what would something like that look like for the research community, particularly since we have a set of norms, as Burton elucidated, for example, that govern our behavior that aren't the same as the open source software community. So we may want, for example, a different basis for our permissioning. So thinking about that, I thought, well, ideally we would like to open our pipelines as widely as possible, catching as many bugs as possible, or increasing our chances of finding error. And that's in general how we work with our paper publications. But we want it to be citable, right? So if you use it or you build on it, we really do want that citation. That's part of our normative structure in the community. So there are many licenses that do that allow very open permissive use, but say you need to cite, you need to attribute. And so that was the sort of guide that I followed in suggesting licenses for different aspects of research that you might actually be releasing to say do really reproducible research. Okay, so I called it the reproducible research standard and said, so there's a Creative Commons attribution license that very much matches our norms. Go ahead and attribute, but do what you like with this, other than making sure that attribution is in there so you use it. And so the Creative Commons attribution license can adhere to things like media, like text, figures, tables, images, and things like that. For software or code, we can't put the Creative Commons license there, but there are similar licenses from the open source software community that are equally as lightweight and essentially say the same thing. Do what you want with this, but make sure you cite me when you actually do, or give me attribution. And so one of them is modified BSD license, another one you saw earlier, MIT license. They're very lightweight licenses that pre-permission people to go ahead and copy, create derivative works, which would mean, say, modify it for their research. Things that are currently illegal, the way copyright law is currently structured, but are very much of what we would want to do. I would love it if you took some of my software and were able to adapt it to some purpose in your research, for example. But copyright stands in the way of doing that. So we need to be able to take these licensing steps. For data is a little more complicated in the way copyright interacts with data. Raw facts themselves are not copyrightable. However, the Supreme Court says original selection and arrangement of the raw facts is copyrightable. And then there's no explanation of how that would interact with modern research in 2016, like what actually is a raw fact, for example. So my suggestion is releasing data to public domain, or if you can attach an attribution license, for example, if you have original selection and arrangement with your software or something, and you can put an attribution license on it. If you don't want to deal with those issues, you can just sort of put a public domain certification on there, like, for example, the Creative Commons 0 license. Okay, so the idea is taking the barriers that copyright and IP law place on the reuse and reproducibility of computational results and making our sharing of these digital scholarly objects more in line, or completely in line, with our scientific norms. Okay. So, as I mentioned, I'm not the only one who's noticed these problems, and I'm assuming if you're sitting here, you've noticed these problems too. So I wanted to mention a few other things that have been happening in various communities who are trying to address these issues. So in 2009, I convened a roundtable when I was a fellow at Yale Law School and brought different members of the community, or different stakeholders together to discuss these issues around access to code, access to data. And they were from many different disciplines and also from funding agencies and so on, and we produced what we called a declaration, then reproducible research, addressing the need for data and code sharing. In computational science, when I say computational science, I mean any kind of research where there's a computer involved in the discovery process itself. In 2012, so looking back now, at what we were saying in 2009, we progressed since then. In 2012, Brown University runs these week-long conferences called ICERM, and you can apply for one, and we did that for reproducibility issues. So in December of 2012, we had a conference very similar but larger than the Yale Declaration conference, and we're able to put together a much longer and more comprehensive set of issues. We enumerated tools, community responses, policy recommendations, licensing IP recommendations, and in our report, setting the default to reproducible in computational science research. So our idea was sharing should be the default way that we're disseminating our research, rather than the exception of people who sort of stepped up and decided to take this extra burden on themselves. And that's not to say that all data can be shared or all software can be shared, but the idea would be if there's a default around openness, then you make exceptions for, for example, data with human subjects or personally identifiable information. Of course, you're just not going to throw that up on the web. But those would be the exceptions that we work with, rather than the default of everything being closed, which is the way it is now. In 2014, folks at Exceed decided to pre-pen onto their annual conference a workshop around reproducibility. So Exceed is a National Science Foundation funded software that provides an interface or sort of middleware layer for users to use some of the very advanced supercomputing centers in the US who may not be natural supercomputing folks. So it sort of makes the submission of jobs and so on easier. So the idea is, well, maybe in that middleware layer, there's ways to capture things like workflows or what the software actually, what's been submitted, what tests have been run, what models have been run, and actually make reproducibility part of that pipeline in a more organic or more seamless way. In a sense, you want to do it almost without bothering the user as much as you can. Okay, we all know in 2013, the Office of Science and Technology Policy of the White House mandated open data, open access through an executive memorandum and executive order. Now, of course, Obama was directly targeting federal agencies and funded research, but it sparked an impetus for us to start being able to reconcile our own practices with those of open data and, in this case, open access as well, which is coming. And there are a number of other agencies that sort of picked up on this, and I'm happy to talk more about that in questions. And these are ongoing and evolving conversations in the funding agencies. Okay, you can see a little bit of it. So NSF, actually, pretty much exactly a year ago, they had a director symposium, Reliable Science, the path to robust research results. So they used like every other R word except reproducible in there, but that is what they were talking about. And that was the first NSF-wide conversation around reproducibility. The different directors within NSF are taking their own initiatives around it. NIH has now their rigor and reproducibility, so you can actually just go to nih.gov/reproducibility and have a look, and they start talking about it. I think it's very interesting to compare and contrast the different approaches the different agencies are making, or even the different directorates in the different agencies, because you'll see NSF talking a little more about computational science a little more, and NIH talking a little more about the empirical science reproducibility. So you start to see those different sort of approaches and lenses come out. Okay, so I'll just mention briefly a study that I did looking at journals, which is another piece. So we see federal mandates, funding agencies starting to take steps, and now the other sort of one other lever would be, well, what are journals actually doing? And they're doing more than what you might think about data and sharing So you might know that science has required code and data availability since 2011. Nature requires data sharing, and their sort of affiliate journals are adopting various instantiations of this policy as well. The Journal of the American Statistical Association, their applications and case studies journal, one of their two journals, now has associate editors for reproducibility as of September 1. I'm one of them, there's 3. And as of September 1, now anything published in JASA ACS has code and data for reproducibility purposes as a requirement made available with the publication. So what Science and Nature have done is their approach was you email the corresponding author after publication, and the author guidelines say they have to give you code and data. So, whether or not you get it is another story. But with JASA ACS now, the next step is really, well, let's have that sort of traveling with the publication so that reproducibility is baked in. ACM Tom's transactions on mathematical software, they have a replicated computational results initiative where they're running the code on the data, making sure that the results are actually correct from the computational sense before publication. Okay, so I have a little bit more on that in publication. So I looked at 170 journals, and I wanted to see what their policies were with regard to code sharing, data sharing, and how they were changing. So I looked at 2011 and then 2012. And we had actually many other pieces in the study too, like open access, supplemental materials, and so on that I don't have time to go into here. But you can see reasonably dramatic shifts, even from 2011 to 2012, around data sharing. So the policies that these publications were enacting basically fell into 5 bins. They had no mention of it at all. They seemed to be oblivious to the issue, so that's one bin. Some of them had language that implied that they thought it was a good idea to share data or share code. Some of them had explicit language that actually encouraged this. As a journal, we encourage the sharing of data and so on. It may or may not affect editorial decisions, so that seemed to be something they weren't willing to sort of take into account, generally speaking. And then there were a few journals that required it as a condition of publication, and when it says barring exceptions, it means, for example, personally identifiable information or whatnot for you can't legally share. And you can see, so the sort of, what I think is kind of the two money numbers, is you can see how we went from about 67% of the journals in this sample ignoring the issue altogether down to 62 approximately in 1 year. And I haven't done the follow-up in the subsequent years, which would be an interesting study, but journals are rapidly taking this on. And code is also, in my opinion, being taken on, but the discussion is far less mature than the discussion around data. So you see similar trends, however, no mention with 83% down to 79%. Still a nice shift, but vast majority of journals not taking on the issues around code. And that's, I think, been reflected in the sort of larger conversation too. Reproducibility issues tend to be discussed in terms of data access, whereas one of the arguments I've tried to make to you today is they need to be discussed in terms of data, code, workflows, all integrated as part of reproducing the final results. It's great to have the data. It's still really impossible to go from data to the output in a publication if you don't have those intermediary steps. Okay, so the ones leading this tend to be the journals with the high impact factors, so arguably they have more kind of leverage over their authors, and they're a little more comfortable making demands on the authors. We don't see these sort of widespread progressive policies yet, but they're getting there. More and more journals are taking this up. If you have supplemental materials policy as a journal, you're much more likely to have a data availability policy. However, transparency or sort of requirements around data and code sharing seem to have no relationship to whether or not it's an open access journal, which I thought was very interesting. You might have seen sort of philosophical alignment between those two, but it seems like they're very different conversations at this point. And as we saw in my 2 brief tables, data policies and also supplemental material policies are far ahead of where we are in terms of software and code access policies. Okay, a couple of more slides. this is something that impacts a larger community. So it's not a discussion that is just happening within the research community itself. We are also seeing issues like crowdsourcing, public engagement. We're making data available, software is becoming available, and it's not something where you need to necessarily or typically provide sort of academic credentials to get in and access. Everyone's kind of able to get in there and start working on it. So you have interesting questions, I think, for the future around, well, how do we ingest these new discoveries that may come from non-traditional sources, for example, from crowds or super keen high school students or whatever it is. And then we also have those legal issues that travel, like how do we address things like privacy and reuse and so on. We're also seeing an enormous amount of discussion around the use of output from data or into policy making and providing evidence that undergirds many of our regulatory structures. So in my mind, this is not yet remotely organized, but it's starting to happen and that discussion is there. So we have this sort of additional interest, evidence-based policy, evidence-based medicine, and so on how the results actually sort of feed into these larger pipelines in decision making. Okay. Data access, software access, persistent linking to publications. I'd love to see that happen, and workflows. So CI standing for cyber infrastructure. What type of computational environments do we need to support this? I don't think it's a question of just making demands on the researcher. It's really a question of providing environments that make this easy and build it into systems and how we do research. Can we link DOIs to within, on the article and on data, on code, and on these objects, citable objects, like someone who uses your software should cite your software, and that should be just a standard practice about how we carry out research. Can we actually make the DOI structure, link these and make them discoverable in the system? How do we protect privacy? How do we operate reproducibly on very, very large data sets or very, very large code bases that are hard to share or inspect? And then our fundamental emphasis on robust methods, stable results, this notion of reliability and reproducibility. Okay. In the interest of time, I'll just move on. A couple of principles. I think, and what I've tried to travel through this talk is how these changes and these adaptations to this, to reproducibility issues, particularly computational reproducibility, needs to follow our scientific norms. It's not a question of changing what science is or how we do science. It's a question of just sticking with the principles that we've embodied for many hundreds of years. When we're developing tools and environments that support research, like for example, even policy, but all of this, we need to have this notion of best practices that are actually embedded in the tools that we're using for scientific research. And these aren't always necessarily well defined, and so there's this evolving conversation about what that actually means. And what I'm calling the holistic approach to cyber infrastructure, so having this idea that it's an entire soup to nuts pipeline that we need to be capturing. It's not just a notion of a data set or even just worse, process data set. We need to go from whatever raw data means in that context, and then all of these computational steps that were visited upon the data we need to be able to capture and share. All of this, of course, is taking place in a very complicated social and political environment, and particularly with federally funded research, you see in Congress, for example, many discussions around how does this play into American innovation or the creation of jobs, and things that, at least for me as a researcher, aren't exactly always on the forefront of my mind when I'm choosing research projects. So there's really this sort of larger context that a lot of our changes are taking place in. And in the introductions, we heard a little bit about how reproducibility is something that starts to be discussed on this larger scale. And that scale includes, folks who fund our work and so on. So we have this kind of larger conversation that's actually going on, that we are embedding all of these changes in. Not to mention researchers who are in incentive structures for promotion and tenure and so on that look more traditional and may not be rewarding efforts around reproducibility. So there's a complicated collective action problem here with many different levers sort of moving. And what I hope that I've been able to do today is show how these different aspects of the collective action problem, these different levers are actually starting to move together, and it's slow, and it takes that coordination to move in concert together. So I'll leave you with a few queries that I would like to see the scholarly record be able to serve to us seamlessly and easily that right now are darn near impossible. So the first one, show me a table of effect sizes and p-values in all phase 3 clinical trials for melanoma published after 1994. That seems like a very reasonable request. It's a very hard thing to query in the scholarly record. It takes a lot of work. Another one, name all the image denoising algorithms ever used to remove white noise from the famous Barber image, and give me the citations of the papers where they were actually used. Also, pretty standard thing. I might want to know, say, for example, machine learning algorithms that were applied on a particular data set. I don't want to apply the same ones. I want to see what's already been done. And who did it, so I can cite them. List all the classifiers applied to the famous acute lymphoblastic leukemia data set along with their type 1, type 2 error rates. So I had a student last semester in the spring where we tried that. That query's hard, and it took us nearly the whole semester to be able to pull that out of the scholarly record. Creating a unified data set containing all published whole genome sequences identified with the mutation in gene BRCA1. Very hard. We also tried that. I would like to randomly reassign treatment and control labels to cases in the published clinical trial X, whatever X might be, and calculate the effect size. And then I want to repeat this many times, create a histogram for effect sizes, and then I could do this for every clinical trial published in, say, 2003, with trial name and histogram side by side. It would be hard. Okay, so there's no reason in a theoretical sense why these should be hard. These are the types of things that researchers would be interested in querying. The queries are at the data level and at the results level, not just at the paper level. So I hope that I've given you some things to think about how we disseminate computational research and what the scholarly record could mean going forward in a world where we have radical transparency around our research. So I'm happy to take questions. Yes.
Very nice talk. I'm from computer science. So in computer science, we have the same problems as you're talking about here. I think that there is a lot, so you touched on it, but I think that there's a lot more that we have to pay attention to. Provenance of the data, changes in the software, and IP. You mentioned a little bit about IP, but derivative works and how do you reconcile that, even if you're using Git or any repository. There's branches already, and so how do you reconcile those things? For academic crowds, I don't know how many people are young versus old here, but there's going to be a tenure conversation. So is the software that you publish, is it going to be part of your tenure? Right. So we are developing a system here at Pitt called OpHub for open curation of software. And one of the things that we are trying to do is not only provide a system that you can package your software and put it up so that you can create the scholarly record we think is going to be a paper that is dynamic. So you click on the graph and then you are taken back to all those things. And then you can manipulate that, expand it a little bit, the graph. And so there is a lot that has to happen.
Yes.
The question is, will people be interested? Because there's tenure, there's publications, how do you actually sell that to the researchers?
Yeah. Well, hopefully I convince some people. No, but so point in case my tenure package is just going in. And I sort of make some discussion, like for example, Research Compendia that I mentioned, that software that I developed in sort of with postdocs and so on, but I sort of make some mention of that, but that's not particularly interesting from a tenure package perspective. However, I think it's very important to research, but they're much more interested in publications that came out of it, so that's really what I talk about. I have heard, at least in statistics, where I'm traditionally from, that tenure committees, promotion committees are starting to ask questions, like where is the software that's traveling with the results? And if the candidate sort of seems totally unaware that this is an important issue, then that's a certain reflection on it. But you're right that there's an enormous amount of work that is done, and I think actually the emphasis that's happened on data sharing is not, I think what you're talking about in terms of the software and the underlying cyber infrastructure and how do we develop these dissemination packages is really where the action needs to be, less so on just are we sharing data where most of the conversation is spent. So I think we're going to be evolving in that direction. I also thought you might ask in your question, what if we can't execute it next year? And probably you can't, right? So there are sort of technical solutions that are coming up around this, but the idea of being able to actually run code on data for years and years and years for every claim in the scholarly record is clearly untenable. So we need to also make decisions around what gets supported at what level and sort of think carefully about this. Much of what I outlined was at an extremely high level. I just said code. But as soon as you sort of pull back, even on data, and you start pulling this back, there's lots there. There's a sort of very complicated issue with lots of levels. So I think we'll be working on this for a while. So things like that are very interesting. You may know there's a fairly new initiative from publishers called Scholix, where they're actually registering, so articles are registered, and through DOIs and so on, but Scholix actually provides registration for data that can then link to publications. So publishers are starting to move in this direction. So I think that goes a little bit to incentives. It's going to happen. The question is how quickly does it, and can we do it in such a way that researchers aren't left behind? I do see, my final point, I do see issues where young researchers will come to me and say things like, particularly ones who have come from the open source software community, they're very much into coding and programming. Many young researchers just have a natural affinity and sort of already are pretty good programmers before they get into school, into grad school, and they say things to me like, I can't believe this isn't here. Like, what do you mean I'm not sharing the code for this paper? I know it's riddled in bugs. And I actually haven't had any good mentorship come to think of it. So I just sort of made this up and no one's checking it, and now it's kind of in whatever prestigious journal. This makes me worried. And some of these researchers have said things like, I'd rather sort of go into industry where I understand the practices better, rather than say, where I don't feel like it's being done in a responsible way. And so I think there's a real danger because we don't hear those voices. I mean, they're very junior grad students and so on, and then if they're exiting and we don't really understand why, that's a real loss to science if we're losing our greatest wings for reasons of just sort of organization and infrastructure. Other questions? Yes, Liz.
So that was great talk, Victoria.
Thank you.
And perhaps building on what's been said already, would you like to say something about what the implications might be for an institution like the University of Pittsburgh in terms of policy, given practically on the table?
Yeah. So I actually think we're at a sweet spot now where the institutions can have an enormous impact. And I think also showcase how supporting research, even with local repositories, which many institutions are taking on, but being able to support the reproducibility from the software through to data and show that holistic soup to nuts understanding of the problem. I'm not sure that the institutional solution is the only solution. It seems to me there should be considerations about interoperability of data in different repositories and so on. So that's something where we can work on that institutionally and across institutions. But policies at the say, at University of Pittsburgh level, it starts to go to issues like what were raised around promotion, tenure, and just knowledge and awareness of these issues as well. So I think that role is key. Sometimes when I give talks like this, I get department chairs and heads come to me and say, what can I do today to start helping my faculty kind of move towards, to capture these younger people who love to code, and that's where they really see the future of their research. And so most of my suggestions are around things like sort of awareness of the issues, making resources available. Do you have like a code or sort of repository equal to your working paper repository, for example? Do you have a modality for people to even sort of make their work available and have it recognized? Even sort of small things that are imperfect. We have to do like software and sort of release early, often in agile, sort of in a very agile way, change and adapt. So even small steps that sort of show an awareness, just putting up a web page saying what people are doing can be enormously impactful. Okay, can I do one more? Sure. Okay.
One more.
I can't hear you, sorry.
I don't understand one aspect of it. That is the copyright issues. For example, when I publish a sub-article, they do not allow us to use that information.
Right.
How do you deal with that?
Yeah, that's a really great question. So, and it unfortunately has a little bit of a long answer. So so when we publish, traditionally we have signed, researchers, authors have signed their copyright over to the journal. There's actually no reason for that. The journal doesn't need it. They've just sort of asked for it and then we've given it for some reason. So I haven't talked at all about the open access issue, which I think is a sister issue in terms of transparency, but a very separate issue with a different kind of conversation around it. We don't need to do that, but we've just kind of kept doing it. So one of the things that concerns me, that I think is very important that we get straight now, is not to let that happen for data and code workflows. We know better. So I don't think Cell would stop you from sharing data.
Yes, they do.
Well, then we need to have a larger conversation about that, because if you aren't allowed to share data that underlies your publications, that seems like a huge, huge problem. And it also seems against the flow of where journals are going as well. So they're going to be like, you know, off in left field where other people are moving towards greater reproducibility. So, but that's something where we need to be up on it and have that conversation so we don't end up with the open access issue happening around data and happening around software. And it's up to us. We don't need to sign those things the way they're put to us.
Please join me again in thanking you.